Welcome to all of you in this session. This session will discuss about the heat transfer. In the subject heat transfer in your undergraduate courses, where we'll talk about the mode of the heat transfer processes, what are the mode of the heat transfer process, and thoroughly we'll discuss regarding this heat transfer process. But before, I think so that you have already studied regarding the thermodynamics and fluid mechanics. So this concept of the thermodynamics and fluid mechanics will come into the picture here. But rather than in the continuation, the subject heat transfer, what we are going to discuss here, that will covers your all kind of the competitive exam, like the GATE examination, any other PSU conducted examination, all of these things it will cover here. Even at the ESE exams also, it will cover. So now we are coming back to the subject. In the thermodynamics, we have seen the two distinct status of the energy. The first one is the energy in transit. Second one is the energy in storage. So what are the stored energy we have seen? That is the internal energy is the stored energy. It is stored in the system. Potential energy, kinetic energy, and the stored energy. Otherwise, the energy in transit, in that cases, heat and work, these two energy are in the transition mode. So there is a system, and other than the system, over that is known as the surroundings. So if we concentrate or focus on what, that is your system, and other than the system, if anything else, that is the surroundings. So if the heat transfer or heat flow from the system to surroundings, so that's why heat is a energy in transit condition. Similarly, the work also. So work and heat, these two kinds of the energy are flowing across the boundary of system and surroundings. So that is the prelude of this subject. But how it is different from the thermodynamics, that we'll see one by one. So directly I'm coming to the slide here. So introduction, we are telling that in case of the introduction, we have already telling regarding these things. So energy having a two part of the energy, that's the energy. Two distinguished status we have seen. The first one is we are talking about the energy in transit. In transit. First status. What are this kind of the energy? That is the heat and work. These two energy, if you're considering a system, it's a system of yours. And other than the system, everything is the surroundings. These are your surroundings. So heat and work can flow through the boundary of system. This is the boundary of the. This boundary may be hypothetical also, or maybe the real. So it is cross, heat and work always cross the boundary. From the system to surroundings boundary, it is always cross. And another mode of the energy you have seen it, another status of energy, that is energy in storage. In case of the energy in storage, which kind of energy? That is the internal energy. Is the in thermodynamics, the internal energy we are defined as a U. We define the internal energy as a U. But now we are coming the heat transfer chapter. In the heat transfer chapter, internal energy, the symbol we will use for the I. I we are taking as an internal energy in heat transfer. Because U will give you the another parameter, that is the velocity. Velocity in x direction we are considering as u. So that will create one confusion between the same symbols. So we are taking I for the case of the internal energy here. So that is the basic prelude. So in thermodynamics, what we have seen, that is a system undergoes through a process from one equilibrium state to other equilibrium state. So a system, let you take initially it was some sort of temperature and pressure. A system temperature, it was like that, it is 100 degrees centigrade, and pressure was, let you say, 1 atmospheric pressure. So that is one state, equilibrium state. System was in equilibrium state. Now I allow the system to undergo through a process. Some processes it happened, and in this process, what it is happening? The temperature is increasing 300 degrees centigrade, and pressure is also increasing 5 bar. So now it is coming a different state, but both state are equilibrium state. That is also was equilibrium state. Previous one, that is the initial equilibrium state, and it is the final equilibrium state. So in the thermodynamics, we have seen from one equilibrium state to other equilibrium state, a system undergoes through a process. And another thing also, thermodynamics, we have seen the first law of thermodynamics were telling, just a recapitulation of this, in a closed cycle. That means in a cycle. So that means a system started from here in first stage, initial stage, and it is going somewhere else, some other equilibrium state, and it is come back to the same. So this is a cycle. It's create a cycle. So in case of a cycle, a system undergoes through a cycle. In that case, the total heat will be equal to the total work. Cyclic integral we are using there. And the cyclic integral, from that is the first law of thermodynamics, and from the cyclic integral we have seen this del Q minus del W is equal to 0. Hence, this del Q minus del W, these two are the path function. This del Q is also path function. It depends on the path, and del W also depends on the path. This for represent the heat, that is represent the work. This two path function difference is implies, give one implication. It implies a point function. It implies a point function. What is that? That is a change of internal energy. That is the from first law of thermodynamics corollary we have got it in that case. So one equilibrium state. Well, so mostly thermodynamics talking about the equilibrium states. If the classical reversible thermodynamics, a system undergoes from one equilibrium state to other equilibrium state, intermediately there are a lot of number of equilibrium states, and this process was very slow process. We know this process is the quasi-static process. Then why heat transfer is coming into the picture? In thermodynamic second law, if you remember this thing, in thermodynamic second law, you have seen a body in the system, let you take it's a system having a very high temperature. Let you take it is a 500 degrees centigrade. And outside surroundings is very low temperature, 30 degrees centigrade. So heat will be transferred. Heat will go from system to surroundings. And this process was a spontaneous process. Spontaneously, heat will go from higher temperature to lower temperature. That we know from the thermodynamics. So heat transfer direction is set by thermodynamic second law. That is in our hand. But how much time it will take to come both at same equal temperature? That is not known by thermodynamics. So thermodynamics does not mention the rate of heat transfer. Heat is transferring from the system to surroundings due to the temperature gradient, due to the temperature difference. But at what rate? At what rate this heat transfer is taking place? How much time is required to both system and surroundings will come in the same temperature or equilibrium state? That is not known from the thermodynamics. So thermodynamics fails to tell it. In such kind of the situation, the heat transfer comes into the picture. With what? With the rate equation. Heat transfer comes into the picture with what? With the rate equations. And as well as some properties also taken, thermal properties. So in the heat transfer subject, we will see the rate equation and as well as the thermal properties. Some dynamic properties also we'll see. So that is the, with these two, the subject is coming as a heat transfer. So we know the heat flow direction. We know the heat flow direction, but at what rate we do in the thermodynamics? Because second law is telling about the direction of the heat flow, but not telling about the at what rate this heat flow will be takes place. That is the most important thing. That's why this subject is coming, heat transfer subject. Now, how many modes of the heat transfer is taking place? What are the modes of heat transfer is there? So now we'll discuss about it. But what is the application of this heat transfer? Why we have applied this heat transfer? Why we require the time requirement? Because industrial, there are a lot of application of heat transfer. In the power industry, there are a lot of several number of equipments, numerous number of equipments in the power industries. Likewise, there's the boiler. Boiler generating the steam. That means from water to steam, it is converting water into the steam. So heat transfer is taking place. How much time it will take to make some amount of the water into a steam? This calculation is from heat transfer. Similarly, the condenser. Condenser is making the steam into the water. So in the power industry, the boiler is just a source and condenser is a sink. And heat engine in between source and sink, and it is producing the power. Other than boiler and condenser, there are a lot of heat exchangers also there. Lot of heat exchanger. What is heat exchanger? We'll thoroughly discuss in this course also later. So power industry, there are enormous application of the heat transfer. Other than the power industry, there are process industry also. Process industry, some biological sector also, medical sector. That means the laser treatment. In the case of the some cancer cell is there. So we have to destroy this cancer cell. by applying the laser. So this laser is converted into the heat and it will completely destroy the particular cell, infected cell. So there are a lot of heat transfer application, and there are so many natural application also there. Sometimes you have seen in the cases we are start our fan for our comfort. So that is also the convectional heat transfer.